And here, our goal was to build a practical and efficient implementation of the GenASM algorithm for multiple computing platforms. Before, we just had ASIC, and we want to compete with state-of-the-art pairwise sequence aligners like EDLib, KSW2, and BiWFA on all of these computing platforms. So to this end, we propose Scrooge, and Scrooge includes 3 novel algorithmic improvements on top of what I just showed, which address some inefficiencies in that algorithm that I'm going to show in a second. And it includes efficient open source implementations for CPUs and GPUs that are all available on GitHub. In particular, Scrooge consistently outperforms GenASM on CPU, GPU, and ASIC by some 2.1 to 5.9x, depending on the hardware. And Scrooge also outperforms state-of-the-art CPU and GPU baselines, including KSW2, EDLib, and BiWFA. So yeah, we just looked at the ASIC of GenASM, and the key question here is, can we do better? In particular, yeah, can we build a more efficient hardware accelerator? And then if you look at these commodity hardware, which GenASM didn't target at all, so commodity hardware would be something you can buy like CPUs and GPUs. And the question here is GenASM suitable to this commodity hardware, or can it be made suitable maybe? So to answer these questions, we started with a memory bandwidth analysis. We plotted a roofline model. So the first question was, does commodity hardware have enough bandwidth for the GenASM algorithm? So the roofline model lets you plot a compute throughput of a given hardware against its memory bandwidth. And then we can, from this chart, look at some interesting insights. So the y-axis here plots throughput, higher is better. We'd always, in the x-axis is operational intensity. So this is just what we computed off of the GenASM algorithm. The desired operating point is always at the peak compute throughput of the given hardware. That's where we'd like to be. And we know that the given algorithm always operates on its vertical line along the operational intensity. Now, the actual operating point of these algorithms is unfortunately bound by the intersection point between the algorithm and its memory bandwidth. So if you check here, there's the intersection point between the algorithm's operational intensity and the memory bandwidth is significantly below the desired operating point. So that's lost performance due to limited bandwidth. If we had sufficient bandwidth, this blue line would be much higher, and the orange and the violet points would meet, but we don't have that unlimited bandwidth in commodity hardware. That's why we're losing performance. And that's the first inefficiency we observe in the GenASM algorithm. So GenASM cannot saturate commodity hardware with computation due to limited bandwidth. So this was off-chip bandwidth that I showed actually. On-chip memory can be much faster than off-chip memory. And in that case, the question to ask is, well, do we have enough on-chip memory to fit all the data, right? And if we can't fit all the data in on-chip memory, then it's not that much of an issue in terms of bandwidth. So let's plot from the data sheets of these 2 recent CPUs and GPUs, the respective on-chip memories of the fastest cache levels. And then we plot against that the memory footprint of the GenASM algorithm. And as you can see in the CPU case, it's already a bit of an issue. The CPU doesn't have enough footprint. It doesn't have enough on-chip memory capacity for the memory footprint. Well, in the GPU case, it kind of barely works out. But once we introduce simultaneous multi-threading, the picture changes significantly. So simultaneous multi-threading, this is called hyper-threading in Intel speak. What this means is you use multiple threads per hardware core. So if you have a CPU core, you want to have 2 alternating threads running on it to constantly have something to work on in your compute units. But having these 2 threads running in the single core means you also need to have 2 problem instances, or in this case, 2 dynamic programming tables in memory at the same time to be able to work on these problem instances. That means your memory footprint doubles and the problem exacerbates. And also in the GPU case, actually, it looks much worse now because GPUs for simultaneous multi-threading don't just need 2 instances, but many, like 4, 5, 6 instances. So this is because they're just designed with massive simultaneous multi-threading in mind. But then the available on-chip memory also on the GPU is nowhere near enough to fit all of GenASM's memory. And this is the second inefficiency we observe. GenASM just doesn't have enough memory footprint, especially when multiple instances are kept in memory for simultaneous multi-threading. Okay, so so we observed that there's some unnecessary work in GenASM as well. In particular, if we check this table again, the traceback starts from this first 0 in the leftmost column, and we observe that there's a significant range there that cannot be reached by traceback. So we have this first 0, and then from here, traceback only goes to the right and upwards. That's always the case, actually. And if that area cannot be reached by traceback, then we can call this unnecessary work because we're computing it, but just never ever looking at it again. Okay, so in summary, we have 3 inefficiencies in the GenASM algorithm: a large memory bandwidth requirement, a large memory footprint, and some unnecessary work. Okay, so to address these inefficiencies, we propose Scrooge. Scrooge consists of memory improvements and efficiency improvement. The memory improvements reduce both the memory footprint and data movement of Scrooge. So we have Sene, store entries not edges, and Dent, discard entries not used by traceback. And then the efficiency improvement eliminates the unnecessary work that we had identified. We call this one early termination. So Sene stands for store entries not edges, and it comes from the observation that so if you look at the single entry over here, what's actually stored by GenASM is not one of these entries, but rather the 3 edges that produced 3 out of the 4 edges that produced this entry. So there are really 3 edges that are stored by GenASM to then be able to trace back where a given 0 came from in here. Now, what we observe is that actually it's sufficient to just store the entry itself, not the ingoing edges. So Scrooge only stores that, which is 3 times less bits than all of the edges. And that out of the box gives us a 3x reduction in memory footprint and data movement. It comes at the slight compute overhead to regenerate the edges that are needed during traceback, but it turns out this is a very minor overhead. Okay, then we have the Dent improvement, discard entries not used by traceback. And this one comes from the observation that traceback here is essentially confined due to a small area in the dynamic programming table. This is due to the windowing heuristic. I didn't introduce this in detail. I would refer to the paper for that. But essentially, it turns out that due to this windowing heuristic, traceback can only go 2 bits to the right in a 4-bit table. And for a large table, it's about for half the bits. And of the remaining bits are never reached, and they do not need to be stored. They do need to be computed because the purple bits depend on them with data dependencies, but they do not need to be stored for later traceback. And just discarding them after computation gives a 4x reduction in memory footprint and data movement. Okay, third, we have this early termination improvement, ET. And the key idea here is that when we build the table top down, we just stop building the table as soon as we find that 0 in the leftmost bit. So recall that the unnecessary work down here was to compute the part of the table down here that can never be reached by traceback. So if we stop building the table as soon as we find that 0 that indicates the edit distance, and then start traceback from there, then the area that cannot be reached by traceback is also not computed, and this eliminates the unnecessary work. We calculate that this is at least 25% on average of the entire dynamic programming table. And when you have very similar sequence pairs, then this is even much more. So it's 25% when you have completely random sequence pairs. And if, let's say, the two strings differ by only one edit or even 0 edits, then we can stop even in the first row immediately and do almost no computation, which makes this highly efficient. So yeah, we implement all of these improvements for both CPUs and GPUs. We open source them as on GitHub, and it's really easy to use library interfaces. Yeah, we open source all of our implementations on GitHub, and this should be really easy to use library interfaces. And our GPU version targets NVIDIA GPUs for reasonably recent compute capability. So yeah, it's all available over here. And of course, we evaluate our implementations quite comprehensively. So we simulate some long reads, we get real short read data, and we evaluate on these recent CPU and GPU architectures, and we also do an ASIC evaluation based on prior logic synthesis. So we plot long read throughput, higher is better. Y-axis is alignments per second. And we observe that on the CPU, Scrooge here in blue outperforms all CPU baselines. And on GPU for long reads, also Scrooge outperforms all baselines as well. In particular, it outperforms GenASM by 2.1x on CPU and 5.9x on GPU. On short reads, we again plot alignments per second on the y-axis, higher is better. And the CPU throughput is again best for Scrooge. It outperforms all baselines. Same thing on GPU again. In particular, Scrooge outperforms GenASM by 3.8x on CPU and 2.4x on GPU. Third, we evaluate ASIC results. So we observe that Scrooge, when implemented as an ASIC, introduces really no significant computation overheads over GenASM, while its on-chip memory is much cheaper than GenASM's due to the memory footprint and bandwidth reductions. It uses 18x less chip area and 18x less power, just the on-chip memory itself, due to these improvements. In particular, then, when we calculate these improvements for the entire chip, this results in Scrooge using overall 3.6x less chip area and 2.1x less power than the original GenASM ASIC. We evaluate everything in much more detail in our paper, including throughput sensitivity to each of our proposed improvements, scaling results, accuracy analysis, and sensitivity analysis to some algorithm parameters. And of course, then we also give a detailed ASIC breakdown in terms of how that area came to be. Yeah, we have our paper on archive. We have our accepted paper on bioinformatics, our archive version that we keep updating with newer results as we have them, and of course, Scrooge on GitHub. So let me conclude by saying, okay, pairwise sequence alignment is computationally costly and a common step in bioinformatics pipelines. GenASM is this prior work, and it's a really promising algorithm for efficient pairwise sequence alignment. Our goal was to build a practical and efficient implementation of GenASM algorithm for multiple computing platforms and compete with state-of-the-art pairwise sequence aligners. To this end, we proposed Scrooge, which includes 3 novel algorithmic improvements on top of GenASM, which addresses some of its inefficiencies, and we introduce efficient open source CPU and GPU implementations of the improved algorithm. We observed that Scrooge consistently outperforms GenASM, such as by 2.1x on CPU, 5.9x on GPU, and has 3.6x better area efficiency when implemented as an ASIC. Finally, we observed that Scrooge consistently outperforms state-of-the-art CPU and GPU baselines, including KSW2, EDLib, and BiWFA. So with that, I'll conclude, and thanks a lot for your attention.